All right, so ready to do some examples from 21.2. Just to review just a little bit about what we've been talking about. Circuits. We had a worksheet over circuits last week. Now this is what a parallel circuit looks like. A parallel circuit is when current is flowing and then it has the opportunity to break and flow into two parallel regions. A series circuit is when energy starts to flow and it goes through one resistor, then another resistor, then another one. It goes through one, then another one, then the current never splits. Or here the current can split amongst two different paths. Here it has to stay along the same path all the way through. And so those were the two types of circuits we had. And if you remember a series circuit, the equivalent resistor is always the sum. It would be an equivalent resistor can be found by simply adding up these three. So resistor 1 plus resistor 2 plus resistor 3. R1, R2, R3. And then the parallel circuit, an equivalent resistor for one of those can be calculated by doing a reciprocal sum of each. So 1 over R1 plus 1 over R2 would equal 1 over the equivalent resistor. All right, so we're going to take what we know about circuits and we're going to combine that information with Ohm's law. Remember, Ohm's law is this formula right here. This stands for voltage equals current times resistance. Voltage, current, and resistance. Voltage is measured in volts. Current is measured in amps. And resistors are measured in ohms, which uses the Greek letter omega, but we refer to it as ohms. So one thing that has been really difficult to wrap my head around in this whole chapter is what's the difference between voltage and electromotive force. And after reading, I come to the conclusion that voltage basically is to an electric current kind of like a water pump is to water. It's what pushes the current through the wire, just like a pump might push water through a pipe. So the voltage is what actually pushes the energy through, and the electromotive force is what supplies the energy to the electrons that get pushed through the thing. So for this particular lesson, they're pretty much interchangeable, so you don't really need to worry about the differences between them for the most part. You'll see in this lesson they sometimes use E here instead of V, and it means the same thing. So for the purpose of this lesson, these two are pretty much just interchangeable. So don't let it freak you out if you see an E in this formula. They are both measured in volts, and they will use them interchangeably here. All right, so our first example is on page 758, and it says a circuit consists of 3 resistors connected in series. So they have a picture of that right here. This is a series circuit. Current's going to flow here through this resistor, then this one, and over to the negative side of the terminal. It's a 24-volt battery, so that's your electromotive force. Another term, now that I'm thinking about it, when I said these here, another thing you might see here is potential difference, because that's kind of the definition of voltage. So if they ask you for or give you potential difference, it means the same thing as voltage. So those 3 words are 3 phrases are going to be interchangeable for us here. All right, so we have a 24-volt battery, which is going to be our electromotive force or voltage. The current is 0.302 amps, and you have 3 resistors of 250 ohms, 150 ohms, and you're supposed to find the resistance on R3. And letter B, we're supposed to find the potential difference across each resistor. So this could be thought of as the potential difference across the whole thing, but they want to know what's the potential difference across each resistor. So we know Ohm's law works, V equals IR, but you can apply V equals IR, Ohm's law, to the whole circuit, and you can also apply it individually to each resistor. And so this formula really has meaning in 4 different things in this circuit: the whole thing, and then each one individually. So they're giving us the voltage for the whole thing, and they're giving us the current for the whole thing. So if I know the voltage and I know the current, I could easily find the resistance in the whole entire circuit. So that would maybe be our first step, is to figure out the resistance for the whole circuit, which would be called our equivalent resistor for the entire thing. All right, so if I were to work that out and solve that, I would have R equals V over I. And so I'm going to work that out on the next page. V equals IR. So we said R, our equivalent resistor for the entire circuit, is V over I. And this was a 24 volt system, and it had a current, remember the variable I is for current, has a current of 0.032 amps. Alright, so if we type that in our calculator, we will get 750 ohms for the equivalent resistors. That's the equivalent over the entire series circuit. Well, if you remember, anytime you have a series circuit where they're going like this one is, I'll redraw it here as to what the picture in the book looked like. We do not know this resistor over here. We do know R1 and R2 are 250 and 150. So this is a 250 ohm resistor. This one's a 150. I'm supposed to figure out R3. That's the first question they asked me, is what's R3? And remember that the equivalent resistor for the whole circuit is the sum of the three resistors, since this is a series circuit. And so I can easily solve for R3 by plugging in what I already know. I figured out the equivalent resistor for the whole circuit was 750. I know that R1's 250 and R2 is 150, and now I need to solve for R3. So 750 minus 250 would be 500, and then 500 minus 150 would be 350. So that is our third resistor, which is the first question that they asked me. So we have figured out the first answer. Now the second question was to find the potential difference across each resistor. So remember me saying that potential difference is another, it's basically the definition of voltage. So it's your V. All three of those. Electromotive force, potential difference, and voltage are measured in volts. So I'm trying to figure out V across each resistor in this picture. So the current which we know stays the same all the way through this thing. The current doesn't divide. It has to go through here, and through here. Now that's different if you have a parallel circuit, because in a parallel circuit the current can split off into other wires. But here my current will stay constant all the way through. My voltage across each resistor can be different depending upon the resistance of each resistor. So I simply need to take the current, which is 0.032, times the resistor, the resistance of each resistor, which I know. I know the resistance on the first one, the second one, and now the third one. Okay, so we are looking for, I'm going to call it voltage 1, because this is going to be the voltage across resistor 1. And so remember that voltage is current times resistor, and my current is 0.032. And so I'm going to multiply that by resistor 1 to find voltage 1, and resistor 1 was 250. To find voltage across resistor 2, I will take current times 150, because that's the amount of resistance that resistor 2 has. And the voltage across resistor 3 would be the current times the resistance of resistor 3, which is a 350. So now I simply type those three in my calculator, and that will be my answer. So the first one comes out to be 8 volts. The second one comes out to be 4.8 volts. And the last one comes out to be 11.2 volts. And so the V here is your units. 8 volts, 4.8 volts, and 4.2 volts is the voltage across each resistor. And that's all for the first example. All right, next example. All right, so the next example is on page 761 in your book, and notice that this is a parallel circuit. You have your battery here. This is the positive side, so your current is going to flow out the positive side of the battery along here, and notice now your current has the opportunity to do 3 different paths. It can come here, here, or here. And so this current is not necessarily going to stay constant all the way through the circuit, because some is going to go here, some is going to go here, some is going to come here. In the end, you'll have the same amount coming out over here. But the amount of current across each resistor can be different since that current can split. All right, so let's see what we know. We know that resistor 1 is 250, resistor 2 is 150, and resistor 3 is 350. And that this is a parallel circuit hooked onto another 24-volt battery. All right, so A is find the total current supplied to the battery, and then the current through each resistor. So I have to find current in all 4 cases. So if I want to find current, remember that voltage is equal to current times resistor. So if I want to know the current for the entire system, then I need the equivalent resistor for the entire system as well. And I know that my voltage is 24. I have 24 volts total, and the volts in this problem, I believe, will stay the same all the way through. The amount of voltage is going to be 24. It's your current that varies this time. In a series circuit, it's your voltage that can vary, where in a parallel, it's your current that varies. All right, so voltage, I'm looking for current. So current is going to be equal to voltage divided by R, and in this case, for the whole system, it's going to be the equivalent resistor. So I know that the voltage is 24. I need to find the equivalent resistor. And so they kind of have it shown to you here. I'll work it out, but this is a parallel circuit. So remember, in a parallel circuit, that equivalent resistor is the sum of the reciprocals. R1, which is 250, plus 1 over R2, which is 150, plus 1 over R3, which is 350. And so now, if you remember, I'm going to need to add these up and then basically do a reciprocal to get this by itself. I don't want to know what 1 over the equivalent resistor is. I want to know what the equivalent resistor is. So I will type these 3 in the calculator and get a number for that, which gives us 0.01352 when you add these up. So now to get the equivalent resistor by itself, I would multiply both sides times Req. And now to get the Req by itself, I would take 1 divided by this. So 1 divided by this will give me an equivalence resistor of 73.96 ohms. So that is the resistance of the entire circuit. All right, so I now know they gave me the individual resistance of each one. Now I know the resistance of the total circuit, which is the first thing they asked me to find, or I guess I take that back. They asked me to find current. But now that I can plug this in here, and that would allow me to find the current. All right, so current is equal to voltage, which is 24, divided by the equivalence resistor, which I just figured out was 73.96. So divide those two, and we get a current of 0.325 amps. Okay, so that's the current, initial current flowing through the whole system. Now I need to find the current across each circuit. So I know the total amount of current flowing through here. When it gets here, some of the current's going to go here, some's going to go here, and some of it's going to go here. So I want to figure out the amount of current that's flowing through each one of those. And I know, keep in mind that voltage will stay constant. The potential difference stays constant all the way through, and the current is going to change on this one. So if I figure this out for each one individually, current is equal to voltage times resistance. And so if I want to know the current on resistor 1, then I would take 24 divided by the resistance of 1, which is 250. And then I want to know the amount of current flowing through resistor 2. I take the voltage, which is constant, divided by resistor 2. So that one's going to be 24 divided by 150. And then for the last resistor, it's the current flowing through it is going to be voltage divided by resistor 3, which is a 350. And so now if you divide all those to figure out how many amps for each one, the first one we get about 0.096 amps. The second one we get 0.16 amps. And the third one we get 0.086 amps. So just to verify that this is the correct answer, remember that we had a certain amount of current, which we figured out here was 0.325 amps. So we have to start off with 0.325 amps traveling through the circuit. Some of it goes here, some of it goes here, and some of it goes here. So the answers that we got for these three should add up to what we had initially. And then when they come back together on this side, they make that same amount going out. So let's add up the three answers we got and see if they add up to the 0.325. And so if you take these three, type them in the calculator, sure enough, the answer you get, 0.3246, will round to 0.325, which is what we got on the previous page. So a good indication there that we did these problems correctly. All right, and this will be your last example. And in this example, it's on page 763 in your book. It says, in the circuit shown in the diagram below, the EMF, which stands for electromotive force, of the battery is 12 volts. So in the previous two problems, they called that potential difference or voltage. And each resistor has a resistance of 450. So this time, these all have the same resistance. Find the current supplied by the battery to this circuit. So they're wanting the current right here, how much current is supplied to this thing initially. Before it has the chance to split right here. So the total amount of current flowing through this system. All right, well, let's see. If I want to know current, once again, we said is I, and current is going to be V divided by R because we get this from Ohm's law and just solving for I. And so do I know the voltage initially? Yes, the voltage or electromotive force was 12. But I do not know the overall resistance. To find the overall resistance, I need an equivalence resistor for the whole thing, for this whole thing right here. Well, I know that this one's 450 and this one's 450, and these two are in series. Whatever current flows through here has to flow through this one, and then all that current has to flow through this one. So they are in series with each other. And so remember that whenever you have a series, that means that you can add up the two. So equivalent resistor 1, I'm going to call this. That's not the same as this equivalent. This one's for the total thing right here. Maybe I should just call that RT for total resistance. And so this one's the equivalent resistor for these two. So that would, since it's a series, you just sum them up. 450 plus 450, which is 900. So these two right here have an equivalent resistor of 900 ohms. Okay, so I have 900 ohms here. So basically, I have current that's flowing through here. Some of the current's going to go here, and some of the current's going to go here. This one the current that flows up here is going to go through a 450 ohm resistor, and the current that flows down here is going through a 900 ohm resistor. So you could assume that more current would flow up here because there's less resistance. It's going to slow the current down going through these resistors, so probably more of it's going to flow up here. So we'll see if that's what happens. So now these two are in parallel. So whenever you have a parallel circuit, to find its equivalent resistor, you have to do the reciprocal. So this one's going to be my total one because this is the last resistor I have to figure out. It's going to be 1 over 450 plus 1 over 900 because these two right here are an equivalent of 900 together. And so then if I add those together and then do the reciprocal to find RT, I will know my total resistance. So if you work this out, you add these together and then multiply both sides times RT and divide 1 by that number, you're going to end up with an equivalent resistor, a total equivalence of 300 ohms. All right, so remember, that wasn't what I was trying to find. I'm trying to find the amount of current flowing through that battery in the beginning. So if I replace this with a 300, I will have 12 divided by 300, which comes out to be a current of 0.04 amps. So I have 0.04 amps flowing through this battery. And that is all. And your problems are assigned on Schoology. You can look there to find those.